So we've spent a little bit of time looking at metallic bonding, ionic bonding, and now we're going to spend a good deal of time looking at covalent bonding. And the reason we spend a lot more time on it is it's just a little bit more complicated than ionic bonding. And instead of like ionic bonding being the transfer of electrons from a metal to a nonmetal, covalent bonding again occurs between nonmetals, and it involves a sharing of electrons. So let's kind of take water, for example. Water is made up of hydrogen and oxygen, so two nonmetals. And oxygen, if we look at the Lewis dot structure of oxygen, it's got six valence electrons. Each hydrogen has one. Now you notice that oxygen isn't happy. It doesn't have a full octet of electrons around it. And hydrogen is fine with two. Each hydrogen does not have that filled valence shell either. But if oxygen were to take one of its electrons and share with hydrogen, and then take another electron and share with the other hydrogen, then let's kind of look at what that dot structure looks at now. Now, if you look at hydrogen here, this hydrogen's got two electrons around it. This hydrogen's got two electrons around it. And this oxygen has eight, a full valence shell around it. So by sharing these electrons, all of the atoms have an octet rule, or have a filled valence shell, I should say. And it's okay that we're double dipping between oxygen and hydrogen. So these two electrons being shared here count for both the hydrogen and the oxygen. And we call this a bonding pair. And then these non-bonding electrons, we call them lone pairs. And then what we do to kind of make this a formal Lewis structure, and we will spend a lot of time on drawing Lewis structures, so this will make a little bit more sense later, is we use these lines to represent a bonding pair of electron. Each line represents two electrons, or a bonding pair. Now let's look at some more examples of this. What I'm going to do is look at some of the diatomic elements, and I'm gonna take a little bit of a rabbit trail here because I haven't really talked much about diatomic elements. Most of the elements on the periodic table exist as a single, as an atom that associates with other atoms of itself, but not formally bonded. There are a handful of elements, though, that exist in nature as diatomic elements, meaning that prefix di meaning two. And these include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I kind of drew them like this because that's like sort of the order or how they would show up on the periodic table. The other reason I drew it, like it kind of forms the number seven. There's seven diatomic elements. And whenever these elements appear in nature, they will exist as with this formula, H2, N2, O2, and so on. So let's kind of look at how chlorine bonds and why it kind of makes sense that chlorine would want to exist as a diatomic element. So here's one chlorine atom with its seven valence electrons. Here's another chlorine atom with its seven valence electrons. If each one had one more, they'd have a full valence shell. So rather than take from one and give to the other, because then only one of them still is happy, they're going to share a pair of electrons and form what's called a single bond between them. The single bond is a sharing of two electrons. Now, I'm going to go to the next page here. Let's take a look at oxygen. So let's draw one oxygen here with its 6 valence electrons, and another oxygen here with its 6 valence electrons. Now, both oxygens need two more each to have a full valence shell. So if I only share one pair, then they're still not happy. So I'm going to share another pair of electrons. And the way that, so like if we were going to keep up with the dots, now there's two sets of dots, two bonding pairs between the two oxygens, and each oxygen has two lone pairs. The way we express this in a Lewis structure is we use two lines. And those two lines are called a double bond. A double bond is a sharing of 4 electrons. Now let's look at one more diatomic element, and that's nitrogen. So nitrogen has 5 valence electrons. So I'm just drawing each, of the two nitrogens with its 5 valence electrons. And again, I'm going to go through and see how much I can share because both of them are 3 electrons short. So I can share one pair, still not happy. I'll share a second pair, not happy there, not quite yet. And I'll share one more pair. I don't know if that makes sense, but one more pair of electrons. So I'm sharing a total of 6 electrons between them. That's going to form what we call a triple bond, which again is the sharing of 6 electrons total between two atoms. Now, before I move on, I want to just kind of talk a little bit about the properties of these single bonds, double bonds, triple bonds, because there is a difference between them if you're sharing more electrons or less. Think about this in terms of bond strength. Do you think sharing more electrons creates a stronger bond or a weaker bond? So the trend for bond strength is that single bonds are the weakest, then double bonds, and then triple bonds are the strongest. So bond strength increases from single bond to double bond to triple bond. Now the opposite is true for bond length. So for bond length, triple bonds are the shortest and single bonds are the longest. Now, what I'm going to be discussing in the next few pages are kind of setting the stage for how we draw these Lewis structures. How do we draw the structures of covalent compounds? And as I said before, there's a lot more in depth than ionic because there's a lot of things we have to know about the individual atoms in order to properly draw the structure of a covalent compound. One of those things is known as electronegativity. You'll see me use the abbreviation EN because I don't like writing that whole word a bunch of times. So EN is the abbreviation for electronegativity. And this does a couple things for us. It helps us predict something known as bond polarity. And I'll get into bond polarity in the next day's lectures. But in the short term, this is going to help us draw Lewis structures. And we'll see why when we start looking at the rules for drawing them. So what is electronegativity? It's the ability of an atom to pull an electron in bonds towards itself. And this is another periodic trend that would be very important for you to know. In general, electronegativity increases going across a row and going up a column. Usually, 99% of the time, we ignore noble gases. The noble gases don't bond very often. We're going to see it maybe pop up every now and then, but it's not a common occurrence. So the most electronegative atom on the periodic table is fluorine. Fluorine is the most electronegative atom. And if we kind of look at why that trend exists going across the row, the effective nuclear charge is increasing as we go across the row. We've kind of hammered that over and over again because we're increasing the number of protons. And then the reason it goes up is we're getting smaller. The electrons are closer to the nucleus. Now, one other kind of important trend that I want to highlight, and we've discussed this before, is let's just kind of look at a few atoms. Let's compare fluorine is the most electronegative, then oxygen, and then chlorine, and bromine, and so on. I'm sorry, nitrogen. And I highlight this because it's important to know that going up or down a column causes a bigger effect in electronegativity than going left to right. Notice if you go from fluorine to chlorine, it goes down almost, what is that, about 0.85 units or so. But going from oxygen to fluorine, or fluorine to oxygen only goes down about half a unit. So going down a column has a bigger effect than going left or right. Now, another important thing that's going to keep on popping up when we start drawing Lewis structures is formal charge and valence electrons. Now, essentially, these are basically just different ways of counting electrons. Both of them are very important for drawing proper Lewis structures, though. Valence electrons tell us if atoms have the correct number of electrons. When I say correct, what I mean is full valence shell. And when we draw Lewis structures, this is one of the most important things that we have to assure in drawing a proper Lewis structure. This is more important than a low formal charge. And what is formal charge? I don't think we have brought that term up yet. Formal charge is kind of like a fictitious number, fictitious charge that tells us if an atom has more or less electrons than its lone atomic state. And ideally, it's best for an atom to have a formal charge of 0. Now, it doesn't mean that it's bad if there is a charge of like -1 or +1. But if you are drawing a Lewis structure and you have the option, number one, for everything to have a full valence shell, that's important. That's the most important. Number two, if you're trying to decide between two structures and one has a formal charge of, say, +1 and one is 0, the correct one will be the one with a formal charge of 0. So here's how we calculate formal charge. And this is a formula you'll need to memorize. It's the number of valence electrons for the atom. So on the lone atom minus the number of non-bonding electrons. So those are the lone pairs minus the number of bonds. All right, so let's look at a few examples. We're going to compare oxygen in a variety of different chemical species. So OH, hydroxide, water, and then a compound called hydronium. Now, hydroxide, if you've memorized your polyatomic ions, you know that hydroxide has a negative charge. And I think he even mentioned when I went over polyatomic ions that the negative charge was on the oxygen. Let's use the calculation of formal charge to prove that. So first thing I'm going to do, let's calculate the formal charge of hydrogen. So hydrogen has one valence electron. It doesn't have any non-bonding electrons. There's no lone pairs around it. And there is one bond to it. Actually, I'm going to draw that bond out. Sorry, I went into OChem mode for a second. And so the formal charge of hydrogen is 0. Now, if I do the same calculation for oxygen, oxygen has 6 valence electrons. If I count the number of non-bonding electrons around it, there's 2, 4, 6. And then it's got one bond to it. And that comes out to a value of -1. And that basically tells you the formal charge is on the oxygen. So it tells you the negative charge is on the oxygen. Now let's do this for water. Again, I'm going to calculate the formal charge of hydrogen. It's the same as before, so value of 0. And then formal charge of oxygen, 6 valence electrons. How do I know it's 6? That's a periodic trend. So make sure you know your valence electrons for each of the columns. It has 4 non-bonding electrons around it. 2, 4. And it has 2 bonds. And that comes out to a formal charge of 0. So in water, oxygen does not have a charge. And then the last one, this hydronium. Again, hydrogen has a formal charge of 0. And for oxygen, number of valence electrons is 6. It has one lone pair or 2 non-bonding electrons right there and 3 bonds to it. And that comes out to a value of +1, which tells you oxygen has the positive charge in hydronium. So when we're drawing um, Lewis structures, in regards to valence electrons, for all of these structures above, oxygen has a filled valence shell. That is the most important thing that you assure for all of your atoms, that they have a filled valence shell. And it's the same as hydrogen as well. Again, hydrogen, since it's such a small atom, hydrogen is happy with 2. And for formal charge, closer to 0 is better. Obviously 0 being the best. But sometimes this is unavoidable, and that's okay. And in general, the formal charge is almost always either +1, 0, or -1. In fact, I don't think we will see anything different in this class. If something has a formal charge and that's not 0, it's usually +1 or -1. Now, before we move on, let's look at the ammonium polyatomic ion. Now, on that table, I want you to memorize ammonium is NH4 plus 1 charge. Let's see if we can figure out where that charge is at. So here's the Lewis structure for ammonium. And if we calculate the formal charge of hydrogen, that comes out to a value of 0. And for nitrogen, well, nitrogen has 5 valence electrons. Notice there are no lone pairs on nitrogen, and there are 4 bonds around it. So by calculating that, we've determined that the positive charge is on the nitrogen. Now, the only way you're going to get very quick at this is to practice it, to do it over and over again. And eventually, you're going to get to the point where you can look at it and not even have to go through the calculation. You'll start to recognize some trends. And this is something that you're not going to just, pick up and then put down when you leave GChem. We're going to talk about formal charge quite a bit in organic chemistry. Now I'm going to kind of go down a little bit of a rabbit trail, and then we'll end up circling back to this when we start drawing Lewis structures. But sometimes Lewis structures aren't good enough to describe some compounds. Now, what do I mean by this? It's best illustrated with an example. We're going to look at nitrite, one of those polyatomic ions I want you to memorize. Now, just kind of take my word for it. Once we start drawing Lewis structures, you'll understand why, this is how the atoms are arranged. But the oxygens are bonded to the nitrogen. I know I'm not showing full octets here. I'm just, drawing a basic skeleton. And what's interesting is that real life experiments have shown that the both nitrogen oxygen bonds are the same. Now, why is that interesting? Well, let's just look at a Lewis structure of nitrogen. Again, kind of take my word for this for right now. It'll become more clear when we actually start drawing Lewis structures. So here's a Lewis structure for nitrate. Okay, so all of the atoms have a full octet. There's a formal charge of -1 on one of the oxygens. There's no way to avoid that. But you might ask yourself, well, why did I draw it like that? Couldn't I have drawn it so that this oxygen was the one that had the double bond and the other one has the -1 charge? So which one is the right one? The answer is both are equally good because both of them have filled valence shells. All the atoms have a full octet and the lowest possible formal charge. So the way we relate these two compounds or these two structures is we call them resonance structures. So it's not one or the other, it's both. And this double-headed arrow is known as a resonance arrow. Now we're going to do a very cursory glance at resonance in this class. We're going to go a lot deeper into OCHEM with resonance. And the real life structure of nitrite is a hybrid, so to speak, of the two resonance structures. Because if you look at at those two resonance structures up there, it's still showing like one has a double bond, one has a single bond. But the experiments have shown that the nitrogen oxygen bonds are both the same. So the way we would draw this hybrid looks something like this, where we have like these dots here. That dot represents like a not a complete double bond, and we have the same thing there. And we use this notation. It's not very common. We won't probably use it very much in general chemistry at all. In fact, when I ask you to draw a Lewis structure, this is not what I want you to show. But the purpose of this shows that these electrons here shows that these electrons are what we call delocalized, meaning they're not localized. They're not stuck between two atoms. Sometimes the electrons are over here, sometimes they're over here. And that backs up the real world evidence that the nitrogen and oxygen bonds are equal to each other. They're not a single bond, they're not a double bond, it's somewhere in between. And that kind of leads me to the last foundational concept before we get into drawing Lewis structures, and that's bond order. Now, the simplest way to look at bond order, it's the number of bonds between two atoms. So if you have something that has a single bond, like chlorine, the bond order, or BO, is 1. Oxygen, which has a double bond, the bond order is 2. And then a triple bond order is 3. You don't get any higher than that. There's nothing, no, there's no quadruple bond or anything that exists. Now, none of those structures have a resonance structure, a resonance form. So let's go back now to nitrite. So I'm just going to quickly draw those resonance forms. And again, the difference is which oxygen is double bonded and which is single bonded. But as I said earlier, the experimental evidence shows that they're the same length, they're the same strength. Bond order helps us kind of justify or gives us a value to assign to that. So bond order can be found by taking the number of bonds and dividing by the number of resonance structures. So if we look at the nitrogen here, there's 2 bonds here, 1 bond here. Same thing over here. 2 bonds here, 1 bond here. So that's a total of 3 bonds around nitrogen. And there are 2 total resonance structures, which means the bond order is 1.5. So again, justifying that the nitrogen oxygen bonds are the same. They're not a double bond, they're not a single bond, they're somewhere in between. That's what that 1.5 bond represents.